The space between stars looks silent, empty and peaceful, but the farther a spacecraft travels from Earth, the more dangerous that darkness becomes. Invisible radiation passes through metal and living tissue. Microscopic dust strikes with devastating energy. Communication delays stretch from hours into years, while rescue becomes impossible. In this documentary, the journey moves deeper into interstellar space to reveal why distance itself becomes the greatest threat. Like the video, subscribe to the channel and begin the voyage into the terrifying silence between the stars. Earth surrounds every departing spacecraft with several layers of protection that have shaped life for billions of years. Near the ground, the atmosphere presses gently against oceans, forests, cities and machines holding gases close while softening the harsh conditions of space. Above the surface, the magnetic field extends far beyond the visible air and guides many charged particles around the planet. Together, these systems create a sheltered region in which radiation is reduced. Temperatures are moderated and human technology can operate with familiar support nearby. The atmosphere is not a sharp wall. It becomes thinner with height fading gradually into the vacuum beyond. In its lower layers, nitrogen and oxygen dominate while water vapor and clouds influence heat and weather. Higher regions contain fewer molecules, but even this thin gas absorbs dangerous forms of solar and cosmic radiation. Ozone in the stratosphere blocks much ultraviolet light. At greater heights, atoms and molecules absorb energetic ultraviolet and X-ray radiation, becoming electrically charged in the process. This upper ionized region affects radio communication and marks part of the slow transition from air to space. A spacecraft rising through the atmosphere crosses a changing environment of pressure density and temperature. Engines must produce enough force to climb against gravity and push through air that resists motion. The vehicle vibrates as it passes through turbulent layers, and its structure carries loads that disappear once the surrounding gas becomes very thin. During ascent, atmospheric drag first increases and then falls away. Heat builds on exposed surfaces, not because space itself is hot, but because fast motion compresses and disturbs the air around the vehicle. Every stage of launch depends on careful control, while Earth remains close below. Beyond the dense air, low Earth orbit still lies inside the planet's wider protective environment. Spacecraft circle the planet at several kilometers per second, moving fast enough to continue falling without reaching the ground. The vacuum there is strong, yet it is not completely empty. Traces of atmosphere remain and slowly reduce orbital speed. Satellites also encounter ultraviolet light, atomic oxygen-charged particles, and repeated shifts between sunlight and shadow. Materials expand and contract with temperature changes. Electronics face radiation that can alter stored information or damage sensitive components. Earth's closeness does not remove danger, but it limits distance from repair tracking and communication systems. The magnetic field provides another layer of shelter. Earth's liquid outer core moves conducting material and generates a broad magnetic structure around the planet. This field forms the magnetosphere, a region shaped by constant contact with the solar wind. The solar wind is a stream of charged particles flowing outward from the sun. When it reaches Earth, the magnetic field redirects much of it around the planet. The sunward side of the magnetosphere is compressed while the night side stretches into a long tail. This shape changes as solar activity rises and falls. Protection within the magnetosphere is uneven. Some charged particles become trapped and travel around Earth in broad regions known as the Van Allen radiation belts. These belts contain energetic electrons and protons that can harm astronauts and equipment. Their intensity varies with altitude, location, and solar conditions. Spacecraft crossing them often pass quickly and use shielding, careful timing, and hardened electronics. Crewed missions in low Earth orbit usually remain below the strongest parts of the belts, although they still receive more radiation than people on the surface. Near the magnetic poles, the field lines guide particles deeper into the upper atmosphere. Collisions with atoms and molecules produce auroras, spreading quiet bands of light across polar skies. The same process reveals that the protective field does not simply stop incoming particles. It redirects traps and channels them. During strong solar storms, the number and energy of particles can rise. Satellites may experience electrical charging, navigation errors, communication disruption, or increased atmospheric drag. Crews in orbit may move to better shielded areas when warnings indicate elevated radiation. Earth also supports spacecraft through a dense network of human systems. Tracking stations measure position and speed. Communication antennas send instructions and receive data. Weather satellites observe storms that may affect launch or recovery. Engineers examine telemetry and respond when temperatures, power levels, or computer behavior change. Crewed vehicles can return within hours or days depending on their orbit and condition. Cargo missions can deliver food, water, tools, and replacement equipment. These forms of support remain part of the protective sphere, even though they are built rather than natural. Mission planners also depend on maps of orbital debris, since fragments of old satellites and rocket stages can cross established paths at high speed. Small course corrections reduce collision risk, while radar networks continue watching objects that cannot be seen. For human bodies, Earth's gravity and environment define normal life. In orbit, weightlessness changes muscles, bones, circulation, balance, and vision. Exercise reduces some losses, but it does not remove every effect. Air and water must be carried or recycled. Carbon dioxide must be removed. Temperature and humidity require constant control. A small failure in a sealed cabin can become serious because the surrounding vacuum provides no breathable reserve. Fire behaves differently in weightlessness, and smoke may not rise in a familiar way. Medical care is limited by space equipment and the need to return safely. The planet remains visually dominant throughout this region. Its curved surface fills windows with clouds, oceans, deserts, and night lights. Radio signals travel with only a short delay. Navigation relies on well-mapped orbits and continuous observations. Rescue is difficult, but it remains physically possible. The atmosphere below can slow a returning capsule, converting motion into heat before parachutes or controlled engines complete the descent. This process is dangerous, yet it provides a natural means of losing speed that does not exist in open vacuum. Earth's protective sphere is therefore not a single boundary, but a connected system. Air absorbs radiation and enables controlled return. The magnetic field diverts much of the solar wind while creating hazardous trapped belts. Gravity keeps vehicles near established routes. Ground networks watch, guide, and supply them. Every kilometer outward reduces some part of this support. Within the nearby region, spacecraft remain exposed to vacuum radiation. Heat changes isolation and mechanical failure, but the planet still surrounds their journey with shelter knowledge and a reachable path home. Beyond low Earth orbit, a spacecraft enters the inner solar system, where the Sun dominates energy radiation and motion. Earth no longer fills most of the view, and the journey unfolds across a broad vacuum shaped by sunlight, gravity, and charged particles. The distance between Earth and Mars changes as both planets follow separate paths around the Sun. A mission cannot travel in a straight line toward a fixed target. It must follow a curved route planned so that the spacecraft and Mars arrive together. The simplest efficient path resembles part of an ellipse around the Sun. The spacecraft leaves Earth with enough speed to enter a new solar orbit. Its route stretches outward until it meets the orbit of Mars. This transfer usually takes several months. During that time, Earth moves far from the departure point while Mars continues along its own orbit. Navigation depends on precise knowledge of planetary positions, spacecraft velocity, and the small forces that gradually change the course. Gravity controls movement throughout this region. The Sun pulls continuously on the spacecraft, while Earth and Mars exert weaker influences that change with distance. The spacecraft does not escape gravity after launch. It remains in free fall around the Sun, following a path determined by its speed and direction. Small engine burns adjust this path. They may last only seconds or minutes, yet an uncorrected error can grow across millions of kilometers. Mission teams compare predicted motion with radio measurements from tracking antennas on Earth. Communication remains possible throughout the crossing, but delay increases steadily. Radio waves travel at the speed of light, and even that speed requires minutes to cross interplanetary space. Commands cannot correct sudden problems immediately. The spacecraft must carry computers able to maintain orientation, manage power, monitor temperatures, and protect essential systems without waiting for instructions. Engineers receive information only after the signals complete their journey, and every response must travel back across the same distance. Sunlight is both useful and dangerous. Solar panels provide electrical power near Earth's orbit where energy is strong outside planetary shadow. As the spacecraft moves toward Mars, sunlight gradually weakens. Panels must be large and accurately pointed towards the sun. Dust damage and poor alignment can reduce output. Batteries store energy when panels cannot meet demand, but capacity is limited. Power must be balanced among communication, navigation, heating instruments, and life support when a crew is present. Thermal control becomes a constant task. Space has no surrounding air to carry heat away by convection. A sunlit surface can become hot, while a shaded surface can become extremely cold. Heat leaves mainly as infrared radiation, and the rate depends on surface material shape and temperature. Spacecraft use reflective coverings, insulation, radiators, heaters, and carefully chosen orientations. Internal equipment also produces heat. If that heat cannot escape, electronics may overheat, while nearby exterior surfaces remain cold. The sun releases more than visible light. Ultraviolet radiation can weaken polymers, darken coatings, and change material surfaces. X-rays can disturb electronics during strong solar events. Charged particles from the solar wind flow through the region at hundreds of kilometers per second. Most are protons and electrons with smaller amounts of heavier atomic nuclei. The solar wind is thin, but its particles can charge exposed surfaces and affect instruments designed to measure weak electrical or magnetic signals. Solar storms create a more serious hazard. Powerful eruptions can send dense clouds of magnetized plasma outward from the sun. Other events accelerate particles to high energies that may reach a spacecraft before slower material arrives. The timing, direction, and strength of these events are difficult to predict completely. Observatories near Earth and around the Sun provide warnings, but a spacecraft between planets may receive different conditions because it occupies another location in space. Radiation can cause temporary computer errors, damage memory, weaken solar cells, and gradually reduce instrument performance. Designers use resistant components, protective shielding, duplicated systems, and software that detects corrupted data. A computer may restart after an abnormal event. Important information may be stored in more than one location. Circuits may include protection against sudden electrical currents caused by energetic particles passing through semiconductor material. For a crewed mission, the same environment affects living tissue. High-energy particles pass through the body and disturb cells along narrow tracks. Shielding reduces some exposure, but heavy shielding adds mass and can produce secondary radiation. When particles strike it, water, food, fuel, and supplies can surround a protected shelter. During a severe solar particle event, the crew may remain there until radiation levels fall. The shelter must still provide air communication, temperature control, and essential equipment. The inner solar system also contains natural dust. Most grains are too sparse to form a visible cloud, but they travel on orbits around the Sun. At interplanetary speeds, a tiny grain can pit a surface or damage a sensitive component. Layered barriers break particles apart and spread their energy before they reach the pressure cabin or critical equipment. Larger objects are uncommon, yet many positions remain unknown, so mission paths avoid recognized concentrations of debris. Orientation is maintained by star trackers, sun sensors, gyroscopes, thrusters and spinning wheels. Star trackers compare patterns with stored maps, allowing the spacecraft to determine where it points. Gyroscopes measure rotation. Reaction wheels turn inside the vehicle and rotate the spacecraft in the opposite direction. Small thrusters remove unwanted momentum and correct the course. Each system depends on power software and mechanical parts that must remain reliable for months. As Earth recedes, the mission depends increasingly on systems already aboard. There are no repair stations along the route. Spare parts are limited and repairs must be possible inside the vehicle. Water must be recovered, air cleaned and waste managed continuously. A minor leak, blocked filter, damaged cable or failed pump carries greater importance when return is no longer immediate. Mars slowly becomes the controlling destination, but it remains a moving point of light for much of the journey. The spacecraft follows its planned solar orbit while engineers refine its path through measurements. The Sun remains bright, the vacuum remains silent, and distance continues to grow. Within this inner region, danger arises not from a single extreme condition, but from the steady combination of heat, cold radiation, delay, dust, limited power, and the absence of help. Past the orbit of Mars, the inner solar system gives way to a wider and colder domain. The Sun still governs every orbit, yet its light spreads across an ever larger area and loses intensity with distance. A spacecraft moving outward enters a region where power becomes harder to collect. Temperatures fall, communication takes longer, and the gravitational influence of the giant planets shapes possible routes. The journey is no longer measured mainly by months. Depending on speed and destination, it may extend across years. Jupiter is the first great obstacle and opportunity. Its mass exceeds that of all the other planets combined, and its gravity reaches far into surrounding space. Mission planners can use this gravity to change a spacecraft's speed and direction. During a carefully arranged flyby, the spacecraft follows a curved path through Jupiter's moving gravitational field. Energy is exchanged with the planet's orbital motion, allowing the vehicle to leave faster or slower relative to the Sun. This technique reduces fuel needs, but it demands precise timing and navigation. The environment around Jupiter is severe. The planet's magnetic field is much stronger than Earth's and traps large populations of energetic particles. These particles form intense radiation belts that can damage electronics, degrade materials, and overwhelm instruments. Spacecraft passing nearby must limit exposure, use radiation-resistant components, and protect vulnerable systems. Even brief passages require careful planning. The strongest regions are avoided whenever possible, since shielding alone cannot remove every hazard without adding excessive mass. Jupiter also carries a broad system of moons and rings. Their paths are well measured, but the space around the planet remains dynamically complex. Gravity from Jupiter and its moons alters trajectories continuously. Small errors before arrival may lead to large differences near closest approach. Navigation teams use radio signals, optical images, and repeated calculations to refine the path. The spacecraft must execute commands accurately because communication delay prevents direct control during the most critical minutes. Beyond Jupiter, sunlight continues to weaken. At Saturn, solar panels receive only a small fraction of the energy available near Earth. Large arrays can still operate, but they must be designed for low light, cold conditions and long service. Some missions rely instead on radioisotope power systems, which produce electricity from heat released by radioactive decay. These systems provide steady power without sunlight, though their output gradually declines over time. Every instrument, heater, transmitter, and computer must share a limited energy supply. Saturn's environment is quieter in some respects than Jupiter's, but it remains demanding. The planet has a strong magnetic field, numerous moons, and an extensive ring system made of ice dust and rock fragments. The visible rings are broad, yet much of the surrounding space is empty. Safe passage depends on detailed knowledge of particle distributions and moon orbits. A spacecraft approaching the planet must avoid regions where even small fragments could strike at high speed. Farther outward, the sun becomes a brilliant star rather than a dominating disk. At Uranus, sunlight is greatly reduced and exterior temperatures settle toward deep cold. Mechanical parts face lubricants that may thicken or freeze. Metals, plastics, cables, and seals respond differently to long exposure at low temperature. Heaters protect batteries, propulsion lines, and instruments, but heating consumes power that is already scarce. Thermal design becomes a balance between preserving essential systems and allowing unnecessary areas to cool. Uranus moves around the Sun with its rotation axis tilted almost sideways. Its unusual orientation changes the geometry of sunlight, seasons, rings, and moons. For a passing spacecraft, this arrangement affects observation plans and communication alignment. The planet's distant location also means that tracking signals are faint. Large antennas on Earth must collect small amounts of radio energy after the signal has crossed billions of kilometers. Data rates fall, so images and measurements may require long transmission periods. Neptune lies still farther from the Sun. Reaching it with current propulsion takes many years, unless planetary alignments provide useful gravitational assists. During such a mission, equipment must survive repeated thermal cycles, radiation exposure. Mechanical aging and software operation over a large part of a human lifetime. Components cannot be replaced. Redundant systems may fail one by one, leaving the spacecraft dependent on fewer working paths for power control and communication. The delay between Earth and Neptune is measured in hours for a round trip. A command sent from Earth reaches the spacecraft only after a long interval, and the reply returns after another. By the time engineers learn that a maneuver has succeeded or failed, the event is already far in the past. The spacecraft must detect fault switch to back up equipment and place itself in a stable condition without immediate assistance. Navigation also becomes more sensitive to small forces, weak pressure from sunlight, tiny gas, leaks, uneven heat, radiation, and minute thruster errors can slowly alter the trajectory. Over years, these effects accumulate. Engineers estimate them using tracking data and models of spacecraft behavior. Radio measurements reveal changes in speed along the line between Earth and the vehicle, while optical navigation compares planets and moons against background stars. The giant planets can assist an outward journey, but their positions rarely form the ideal sequence. Each planet follows its own orbit, and useful alignments occur only at particular times. A missed launch opportunity may require years of waiting or a different route. Faster trajectories demand more energy and create greater challenges during arrival or flyby. Slower routes reduce some propulsion needs, but increase the period during which systems must remain functional. Human travel through this region would magnify every difficulty. Supplies must last for years, radiation exposure accumulates, and medical emergencies remain distant from Earth. Artificial gravity could reduce some health effects, but it adds mechanical complexity. Psychological strain grows as communication becomes delayed, and the home planet appears as a faint point of light. The vehicle must operate as a closed habitat with no realistic rescue. Past the giant planets, the solar system no longer offers regular destinations, abundant sunlight, or nearby support. The sun remains the central source of gravity and energy, but its practical presence weakens. Spacecraft move through darkness with limited power, delayed communication, aging machinery, and no external maintenance. Distance steadily transforms ordinary engineering problems into permanent risks, because every failure must be managed with what remains aboard. Beyond Neptune, the solar system opens into the Kuiper Belt, a region of icy bodies, dwarf planets, fragments, and dust. It is not a crowded field of packed objects. Most of its volume is nearly empty, and neighboring bodies may remain millions of kilometers apart. A spacecraft crossing this region sees darkness, distant stars, and the weakened sun. The danger comes less from constant collision than from uncertainty, cold distance, and the difficulty of detecting small objects far ahead. The Kuiper Belt begins near the orbit of Neptune and extends outward for billions of kilometers. Its members are remnants from the early formation of the solar system. Many contain frozen water, methane, ammonia, carbon monoxide, and other volatile substances. At such low temperatures, these materials behave like rock, Sunlight is too weak to warm most surfaces significantly, so ancient ices can survive for billions of years with gradual change. Pluto is one of the largest bodies in this region. It follows an inclined and elongated orbit and carries several moons. Its surface includes nitrogen ice, methane, ice water, ice mountains, plains, and signs of geological activity. Pluto shows that a distant world can remain complex even with little sunlight. Similar complexity may exist on other large Kuiper Belt objects, although many are too small and distant for detailed study. The population of the Kuiper Belt is divided into orbital groups. Some bodies remain in stable patterns influenced by Neptune's gravity. Others follow more tilted or stretched paths. A technical term for these repeating gravitational patterns is orbital resonance. It means that the orbital periods of two bodies form stable relations. Pluto, for example, completes 2 orbits around the Sun during the time Neptune completes 3. This arrangement prevents close approaches despite their crossing orbital distances. Neptune, therefore, shapes the region without filling it. Its gravity has scattered some objects outward, trapped others into resonances, and removed bodies from unstable paths. Over billions of years, these interactions produce a complicated map of orbits. A spacecraft moving through the region must follow a path calculated against this background. Large objects attract from Earth, but smaller bodies may remain undiscovered until they are relatively close. Weak sunlight makes observation difficult. A small object reflects a tiny amount of light, and its dark surface may absorb most of what reaches it. Telescopes detect many Kuiper Belt bodies by photographing the same field repeatedly and looking for slow motion against distant stars. Their distances and orbits are then estimated from repeated measurements. These estimates improve over time, but uncertainty remains greater for faint objects observed across short intervals. For a spacecraft, onboard cameras face similar limits. A dark body may not become visible until late in the approach. Radar is impractical across distance because the returning signal would be extremely weak. Navigation depends mainly on known trajectories, optical imaging, and cautious planning. Mission routes avoid predicted positions of larger objects, while shielding protects against small grains that cannot be tracked individually. Dust density in the Kuiper Belt is low, yet impact speed gives even tiny particles importance. A grain striking a spacecraft at many kilometers per second releases concentrated energy. Outer layers may vaporize or fracture. Instruments with exposed surfaces are especially vulnerable. Layered shields can break up particles and spread the impact, but no shield is perfect. The spacecraft must balance protection against mass because every added kilogram requires more launch energy. The cold is persistent. Far from the sun, exposed surfaces lose heat until they reach very low temperatures. Electronics, batteries, propulsion systems, and moving parts cannot function safely if allowed to cool without control. Radioisotope heat sources and electrical heaters protect essential components. Insulation slows heat loss. Equipment may be placed close together so that waste heat from one system supports another. Areas without critical functions may remain much colder. Power is equally restricted. Solar panels receive only a small fraction of the sunlight available near Earth. Large arrays could collect more energy, but they add mass complexity and structural risk. Most deep missions rely on radioisotope systems. These systems are steady and durable, but their electrical output slowly falls as radioactive material decays and components age. Mission teams may shut down instruments, reduce transmission schedules, or alternate operations to conserve energy. Communication becomes a slow exchange. Signals need several hours to travel between the spacecraft and Earth. Large ground antennas collect faint transmissions, often at low data rates. A single image may require long periods to return. Commands are prepared because mistakes cannot be corrected quickly. The spacecraft must manage routine functions independently and enter a safe state when it detects unusual temperatures, orientation errors, or power problems. The Sun remains useful for navigation, but it appears smaller and less intense. Star trackers provide orientation by comparing observed star patterns with stored maps. The spacecraft's position is estimated through radio tracking and images of known bodies. Small thruster burns correct the course. Because each adjustment consumes limited fuel, planners avoid unnecessary maneuvers. A fuel leak or failed thruster could end the ability to point antennas, control rotation, or reach a target. There are few opportunities for assistance. No atmosphere slows a spacecraft, and no established station provides supplies or repairs. Kuiper belt bodies have weak gravity, so approaching one requires precise control rather than heavy braking. But departure and redirection still consume fuel. A flyby offers only a brief observation period after years of travel. Missing the planned path by a small distance can reduce the scientific return permanently. Human travel would make the region far more difficult. A crew would need reliable life support for many years, heavy radiation protection, medical capability, food production, and a stable source of power. The darkness and delay would separate the travelers from ordinary contact with Earth. Emergency return would be impossible within any useful time. The habitat would need to remain functional without replacement parts beyond those carried aboard. Across the Kuiper belt, space becomes wider, colder, and less forgiving. The icy bodies preserve records of early planetary formation, but they offer no natural shelter. Their sparse distribution does not remove danger because unseen fragments, failing equipment, dwindling, power-delayed communication, and limited fuel continue throughout the crossing. The spacecraft remains surrounded by emptiness, while every useful resource stays inside its hull. The Kuiper belt thins into a broader frontier where the Sun's influence becomes difficult to define by sight alone. No bright wall marks the boundary, and no sudden darkness appears. Instead, the outward flow of solar particles gradually loses strength as it presses against material between the stars. A spacecraft approaching this region enters a changing environment shaped by pressure, magnetic fields, and particles moving in different directions. The central feature is the heliopause, the boundary where the solar wind can no longer continue outward freely. The solar wind begins in the Sun's outer atmosphere. It carries electrons, protons, and magnetic fields away from the Sun in all directions. Near the inner planets, this flow moves rapidly and remains dominant over the thin interstellar gas beyond. As it travels outward, its particles spread across a larger volume. The flow becomes less dense while its pressure slowly falls. It still carries energy and magnetic structure, but the surrounding interstellar medium pushes back with its own gas-dust magnetic field and motion. Before reaching the heliopause, the solar wind crosses a region called the termination shock. A shock is a narrow transition where a flowing material changes speed, pressure, and temperature. At this boundary, the solar wind slows from supersonic motion to a lower speed. Supersonic means that the flow moves faster than disturbances can travel through it. After crossing the termination shock, the particles remain part of the solar environment, but their movement becomes slower, hotter, and more irregular. The region beyond the termination shock is known as the heliosheath. It surrounds the outer solar system like a broad, uneven layer. Its exact shape is influenced by the Sun's motion through the local interstellar material and by magnetic fields on both sides. Measurements indicate that the heliosphere is not a simple sphere. Its boundary may be compressed in the direction of motion and extended elsewhere, although the detailed form remains uncertain. Different models produce shapes ranging from a long tail to a more rounded structure. Within the heliosheath, the solar wind no longer moves in the simple outward pattern found closer to the Sun. Particles are redirected, heated, and mixed through changing magnetic conditions. The flow may become turbulent, meaning that motion develops irregular swirls and fluctuations across many scales. A spacecraft moving through this region measures changing particle densities, magnetic directions, and energy levels. These changes help scientists identify where one region ends and another begins. The heliopause itself is defined mainly by the balance between solar and interstellar pressures. On one side, particles and magnetic fields originate from the Sun. On the other, material belongs to the space between stars. The boundary can move as solar activity changes. When the Sun releases stronger winds and magnetic disturbances, pressure within the heliosphere increases. Years later, those changes reach the distant boundary and may shift its position. The heliopause therefore breathes slowly rather than remaining fixed. Crossing the heliopause does not mean leaving all solar influence behind. The Sun's gravity continues far beyond this region and sunlight remains detectable. Large icy bodies and distant comets still orbit the Sun at much greater distances. The heliopause marks a particle and magnetic boundary rather than the end of the solar system in every sense. For a spacecraft, however, it represents a major change in the surrounding medium. One clear sign of the crossing is a decline in particles linked to the solar wind. At the same time, galactic cosmic rays become more common. These energetic particles come from outside the solar system, often from processes associated with exploding stars and other powerful events in the galaxy. The heliosphere blocks or redirects part of this radiation. As a spacecraft approaches its outer boundary, that protection weakens, and instruments record a larger number of high-energy particles. Galactic cosmic rays are difficult to shield against because they can carry great energy. Some are single protons, while others are the nuclei of heavier atoms. When they strike spacecraft materials, they can pass through, break atomic nuclei apart, or create showers of secondary particles. Electronics may experience errors and detectors may record false signals. Over long periods, materials and components receive cumulative damage. A human crew would face increasing risks to cells, organs, and genetic material. Magnetic measurements also change near the heliopause, although the pattern is not always simple. The magnetic field carried outward by the solar wind may remain partly connected to the Sun. Beyond the boundary, the local interstellar magnetic field becomes more important. Observations show that the direction can change less sharply than some early models expected. This suggests that magnetic fields on both sides may align, bend, or interact in complicated ways. The density of ordinary matter also changes. Interstellar space is extremely thin, yet it can contain more neutral atoms than the outer solar wind. Some neutral particles pass through the heliopause without being strongly affected by magnetic fields. Charged particles respond more directly to those fields and to electric forces. Instruments, therefore, distinguish among particle types, energies, and directions to understand the crossing. Communication with Earth remains possible, but signals are extremely faint. Power supplies have weakened after decades of operation, and instruments must be selected carefully. Commands require many hours to arrive, while data returns slowly. The spacecraft cannot turn quickly from one task to another without consuming limited energy and fuel. Every measurement near the boundary depends on systems that have survived far longer than most machines on Earth. Scientists also study energetic neutral atoms produced when charged particles exchange electrons with neutral gas. Because these atoms travel without following magnetic field lines, they preserve information about distant interactions. Detectors can use them to build indirect maps of the heliosheath, revealing pressure patterns that no spacecraft can sample. These maps remain limited, but they clarify the boundary's structure over time. The heliopause is therefore both a physical boundary and an engineering test. It separates two particle environments, but it does not provide shelter resources or a clear destination. The Sun's protective influence declines, galactic radiation rises, and the surrounding magnetic structure becomes less familiar. A spacecraft crossing this region moves beyond the direct dominance of the solar wind while remaining dependent on aging equipment, distant communication, and a small reserve of power carried from a much warmer world. Beyond the heliopause, a spacecraft enters interstellar space, the thin material that fills the distances between stars. The change is not visible. Darkness remains dark. The sun remains and distant stars keep their positions. Yet instruments detect a new balance of particles, fields, and radiation. The outward solar wind no longer controls the surroundings. Instead, the spacecraft moves through gas and dust shaped by the wider galaxy. Interstellar space is often described as empty, but emptiness here is relative. Even its thinnest regions contain atoms, ions, electrons, microscopic grains, magnetic fields, and energetic particles. An ion is an atom that has gained or lost electrons and therefore carries an electrical charge. Neutral atoms carry no overall charge. These two forms of matter respond differently to magnetic and electric forces, creating a complicated mixture that cannot be understood as a simple gas. The density is extremely low. In many regions, only a few particles occupy each cubic centimeter, and some volumes contain fewer. This is far below any vacuum produced naturally at Earth's surface. A spacecraft does not feel wind in the ordinary sense because too few particles strike it at any moment. Over great distances, however, even this sparse material matters. Every collision transfers a small amount of energy and momentum to the vehicle. The surrounding gas includes mostly hydrogen, the lightest and most common element, with smaller amounts of helium and heavier elements. Some of this gas remains neutral, while some is ionized by ultraviolet radiation collisions and ancient stellar activity. A thermometer exposed directly would not behave as it does in dense air. The spacecraft instead reaches a temperature determined mainly by sunlight, internal heat surface properties, and radiation into space. Although sunlight is weak, equipment still generates heat. Insulation keeps important systems from cooling too rapidly, while radiators release unwanted energy. Thermal control remains difficult because different parts of the spacecraft may face the sun, deep space, or warm machinery. No surrounding atmosphere spreads heat evenly. The interstellar magnetic field becomes a central part of the environment. It is far weaker than the magnetic field near Earth, but it extends across enormous distances. Charged particles spiral around magnetic field lines and move differently depending on their energy mass and charge. The field can guide particles, bend their paths, and create uneven regions of pressure. A spacecraft measuring it must separate genuine signals from electrical noise produced by its own equipment. Interstellar plasma is the charged component of the gas. Plasma behaves collectively because electrical and magnetic forces connect the motions of many particles. Even when collisions are rare, disturbances can travel through the plasma as waves. Changes in density or magnetic direction may pass across large distances. Instruments record these changes through particle detectors, magnetometers, and antennas sensitive to plasma oscillations. Neutral atoms move more freely across magnetic boundaries. Some enter the heliosphere while others collide with charged particles and exchange electrons. These interactions create new ions and energetic neutral atoms. The processes are quiet and sparse, but they reveal how solar and interstellar material meet. Beyond the heliopause, the balance shifts toward particles that belong to the surrounding galactic environment. Cosmic radiation also becomes more intense. The heliosphere no longer provides the same degree of deflection. High-energy protons and atomic nuclei arrive from many directions. Their paths have been altered repeatedly by magnetic fields in the galaxy, so their exact sources are difficult to trace. Some are associated with supernova remnants and other energetic environments, but individual particles usually carry no simple record of their origin. When these particles strike a spacecraft, they may pass through several layers of material. They can disrupt computer memory damage sensors and change the structure of electronic components. They can also collide with atomic nuclei in the shielding and produce secondary particles. Adding more material does not always reduce every form of radiation in a simple way. Protection requires careful choices of composition, thickness, and placement. For living tissue, long exposure creates a more serious problem. Cosmic rays can damage molecules inside cells, including genetic material. The biological effect depends on particle type, energy path, and the organs exposed. Some damage is repaired naturally, while some may remain. Thick stores of water or food can provide useful shielding, but a practical spacecraft cannot carry unlimited mass. In interstellar space, exposure continues without a nearby planetary field or atmosphere. Dust grains are much less common than gas atoms, yet they present a distinct mechanical danger. A grain may consist of silicates, carbon-rich material, metal compounds, or ice. At ordinary spacecraft speeds, small impacts slowly wear exposed surfaces. At higher interstellar speeds, the energy rises sharply. A grain too small to see from a distance can create a hot burst fracture, shielding, or send fragments deeper into the vehicle. Detection is difficult because the grains are dark, tiny, and widely scattered. A forward shield can absorb repeated impacts while separate layers spread the energy. Sensors may count strikes and estimate local density. Course changes offer little protection because the dust is distributed through space rather than concentrated in a single, visible obstacle. The safest design depends on speed shield mass and the expected number of impacts. Navigation remains tied to Earth through faint radio signals, but the delay continues to grow. The Sun becomes less useful as a bright reference, while star trackers remain important for orientation. Small uncertainties in speed or direction accumulate over long periods. A leaking valve, uneven heat emission, or unnoticed impact can alter the path by a tiny amount that becomes significant across vast distances. The immediate interstellar environment offers no surface atmosphere or natural refuge. Its dangers are diffuse rather than dramatic. Gas atoms strike one by one, dust arrives without warning, radiation passes through structure and tissue. Magnetic fields bend charged particles across distances too large to see. The spacecraft moves onward through a medium that appears empty to human senses, but remains physically active at every scale. Entering interstellar space, therefore, removes one of the last broad protections associated with the Sun. The vehicle now depends almost entirely on its own shielding power, navigation, and repair capacity. Nothing nearby can replace a failed system. The surrounding matter is thin, but the journey is long, allowing small effects to accumulate until they shape survival. The local interstellar cloud surrounds the solar system with a thin mixture of warm gas ions, electrons, dust, and magnetic fields. It is one of several small clouds moving through the larger cavity around the Sun. Although the cloud is far less dense than any atmosphere, it is denser than some neighboring regions of interstellar space. A spacecraft traveling outward remains inside this material for a long time because the cloud extends across several light years and the vehicle moves only slowly compared with that distance. Its calm structure can still vary over time as pressure, ionization, and magnetic conditions change across distances far larger than a single spacecraft can directly sample. The cloud does not appear as a bright object against the stars. Its matter is too sparse to scatter much visible light, and its boundaries are not sharp. Scientists infer its presence by studying the absorption of starlight, the motion of neutral atoms entering the heliosphere, and the behavior of nearby interstellar gas. Different measurements reveal slightly different structures, so the exact shape and edge of the cloud remain uncertain. It may contain uneven patches rather than a smooth distribution. Most of the cloud consists of hydrogen and helium. Some atoms remain neutral, while others have lost electrons and become ions. The gas is described as warm because its particles move with energies corresponding to several thousand degrees Celsius. This temperature does not make the cloud feel hot. In the ordinary sense, the density is so low that very few particles strike a surface at one time. Heat transfer by direct contact remains extremely weak. The cloud moves relative to the Sun. Neutral atoms flow into the heliosphere from a preferred direction, while charged particles respond to magnetic fields and interact more strongly with the solar wind. This relative motion helps define the pressure on the heliosphere and influences the shape of its outer boundary. A spacecraft beyond that boundary encounters the same general flow more directly, without the solar wind dominating the local particle environment. Hydrogen atoms are easily ionized by ultraviolet light and by collisions with energetic particles. Helium atoms require more energy, so a larger fraction may remain neutral. The balance between neutral and ionized matter depends on radiation from nearby hot stars, cooling processes, and exchanges between particles. The cloud therefore contains both ordinary gas and plasma. These components occupy the same region, but do not always move in exactly the same way. The magnetic field threading the cloud is weak, yet it shapes charged particles across large distances. Ions spiral around field lines, while electrons respond even more strongly because of their smaller mass. Disturbances in the field can alter particle motion without requiring frequent collisions. A spacecraft measuring the environment records slow changes in direction and strength, but its own electrical systems can create interference. Sensitive instruments are often mounted away from the main body to reduce that problem. Dust grains form a small part of the cloud's mass. They may contain silicates, carbon compounds, metals, and traces of ice. Some grains are large enough to pass through the heliosphere, while smaller charged grains can be diverted by magnetic forces. Their distribution is uneven, and their origins include old stellar winds, supernova debris, and material processed through earlier generations of stars. Each grain carries a record of chemical history, even though it presents a hazard to a fast spacecraft. At low speed, impacts from individual atoms produce only tiny effects. Across years and decades, however, gas can erode exposed surfaces, alter optical coatings, and affect delicate instruments. At higher speed, the same particles arrive with much greater energy. Hydrogen atoms can penetrate shallow layers, create defects in materials, or generate secondary radiation. Dust grains become still more dangerous because their mass is concentrated into small projectiles. A forward shield must therefore protect against both dust and gas. Thick outer layers absorb impacts, while gaps and additional layers spread fragments before they reach the pressure hull. Materials rich in hydrogen can reduce some kinds of radiation, while strong metals or ceramics resist mechanical damage. No single shield solves every problem. More protection increases mass, and greater mass demands more energy for acceleration and later deceleration. The cloud also contributes to background radiation conditions. Galactic cosmic rays pass through it with little obstruction because the gas is so thin. Magnetic fields may bend their paths, but they do not remove the steady exposure. Energetic particles strike electronics and living tissue throughout the crossing. Their effects accumulate with time, so a slow journey can receive more total radiation even when the environment remains quiet. Communication with Earth continues through radio waves, yet the growing distance reduces signal strength. Large antennas aboard the spacecraft and on Earth must point with great accuracy. A slight pointing error can interrupt contact. Data moves at limited rates, and corrections arrive only after long delays. The vehicle must monitor its own power, temperature, attitude, and damage without expecting immediate guidance. Power remains one of the central limits. Sunlight is now extremely weak, so long missions depend on stored energy, radioactive decay, or other durable sources. every year, reduces the output of aging equipment, heaters protect instruments from cold, transmitters consume energy during contact, and navigation systems must operate even when scientific instruments are inactive. Energy management becomes a permanent choice among functions rather than a temporary emergency. For a human crew, the local interstellar cloud offers no usable air, water, or shelter. Its hydrogen is too thin to collect efficiently with ordinary technology at modest speeds. Life support must recycle nearly all internal resources. Food production, waste processing, medical care, and radiation protection must continue without outside supply. Even a minor loss of water or atmosphere becomes serious because replacement material is not available nearby. The cloud's quiet appearance hides the importance of duration. Its particles are sparse, its field is weak, and its dust is rare. But the crossing extends across distances that current spacecraft cannot cover quickly. Small forces act without rest. Materials age, shields erode, power declines, and navigation errors accumulate. The local interstellar cloud therefore becomes a long test of endurance where survival depends less on avoiding one sudden event than on preserving every essential system through an environment that never truly stops touching the spacecraft. The local interstellar cloud occupies only a small part of a much larger cavity called the local bubble. This broad region surrounds the Sun for hundreds of light years and contains gas that is thinner and hotter than the material in many neighboring clouds. Its boundaries are irregular rather than spherical, and its shape reflects a long history of stellar winds, supernova explosions, magnetic pressure, and nearby clouds. A spacecraft leaving the local cloud would still remain inside this larger cavity for immense distances, moving through an environment that appears empty while carrying the marks of ancient violence. The local bubble is identified through several kinds of observation. Astronomers compare starlight absorption map dust that reddens distant stars and study faint X-ray emission. These measurements reveal a region with relatively little neutral hydrogen and dust near the Sun. The cavity is not completely empty, and its contents are not uniform. Thin clouds, filaments, and denser walls occupy parts of the volume, while other areas contain rarefied plasma. The hot gas within the bubble may reach temperatures of about 1 million degrees Celsius. Such a temperature describes the average kinetic energy of particles, not the heat that a spacecraft would feel through contact. The density is too low for rapid heating. A surface exposed to this gas receives very few particle impacts compared with any atmosphere. Its temperature depends mainly on radiation internal power, sunlight, and heat loss into space. The bubble likely forms through multiple supernova explosions and powerful winds from massive stars. A supernova releases enormous energy and drives a shock wave through surrounding gas. One event can heat, compress, and accelerate interstellar material across many light years. Several explosions over millions of years can sweep gas outward and leave a broad cavity. Observations indicate that a group of massive stars moving through the solar neighborhood may have produced some of these explosions. The exact number, timing, and locations remain uncertain because evidence comes from moving stars, radioactive traces, gas structures, and galactic models. The outer walls of the local bubble contain denser material pushed aside by these old events. Dust and gas gather where expanding shocks meet surrounding clouds. The walls are uneven with channels connecting to other low-density regions. In some directions, the boundary lies relatively near the Sun. In others, the cavity extends much farther. This geometry makes conditions depend strongly on route. A route through a thinner channel may reduce dust exposure, while a path near a dense wall brings more gas and magnetic disturbance nearby. Inside the bubble, plasma dominates much of the thin gas. Electrons and ions move through weak magnetic fields and rarely collide. Their collective behavior supports waves, pressure changes, and large-scale motion. Magnetic fields can become compressed along cavity walls or stretched through the interior. Their direction may change gradually across space, and local disturbances can alter how charged particles travel. For navigation, the local bubble provides no obvious landmarks. Its gas is invisible from a spacecraft window, and its boundaries are too broad to resemble walls. Position must be determined through observations of stars, pulsars, and distant radio sources. A pulsar is a rapidly rotating neutron star that emits regular pulses of radiation. Several pulsars can help estimate position and motion, although instruments require precise clocks and long observations. The low density reduces ordinary drag, but it does not remove material hazards. Gas particles strike the forward surface according to the spacecraft's speed. At modest speeds, the effect is small. At a significant fraction of the speed of light, even hydrogen nuclei carry enough energy to damage materials and create radiation. The spacecraft moves through a thin beam concentrated by its motion. Dust remains rarer than gas, but more destructive per impact. The bubble contains less dust than dense interstellar regions, yet some remains. A single grain encountered at high speed can release energy in a tiny area, producing plasma heat fragments and structural shock. Forward shielding must therefore remain thick and layered even in a cavity known for low density. Cosmic rays continue to pass through the bubble from the wider galaxy. The hot gas does not absorb them effectively, and the weak magnetic field only changes their paths. Some lower energy particles may be influenced by local magnetic structures, while higher energy particles cross almost unhindered. Their arrival remains steady, though individual impacts are unpredictable. Radiation damage accumulates in electronic systems. Memory cells may change, state sensors may lose sensitivity, and insulating materials may degrade. Redundant circuits and error-correcting software reduce the risk of sudden failure. Over centuries, even hardened components change through radiation, temperature cycles, and material aging. Crossing the local bubble requires systems that can be repaired, replaced, or rebuilt from stored materials. Power production becomes increasingly detached from the sun. Radioisotope sources decline over decades, and conventional reactors require fuel cooling, shielding, and maintenance. A crewed vehicle needs long-lived energy to support air circulation, water recovery, food production, lighting, computing, and propulsion control. Waste heat must still be released through radiators whose exposed surfaces remain vulnerable to dust and radiation. Communication with Earth weakens as distance grows across light years. Radio signals spread and antennas must become larger or transmissions more powerful. The delay changes from hours to years. A spacecraft message describes conditions Earth cannot influence in time. Mission control becomes a distant source of information rather than an active guide. The vehicle must carry its own scientific records, engineering knowledge, medical expertise, and decision systems. For human travelers, the local bubble is not an open road but a prolonged isolation chamber. The gas is too thin to breathe or collect easily. No nearby planet offers shelter. No repair station exists. The habitat must maintain pressure while protecting its interior from radiation and impacts. Every seal pump, cable, processor, and biological system becomes part of a closed world. The local bubble, therefore, combines emptiness with duration. Its hot plasma transfers little heat, its low density produces little drag, and its broad cavity contains fewer dust grains than denser regions. Yet the crossing extends across hundreds of light years. Over such distance, rare impacts become expected. Weak radiation becomes cumulative, and tiny navigational errors become large separations. The environment remains quiet, but the scale of the journey turns quiet conditions into a severe test of endurance. Interstellar dust appears insignificant when compared with planets, stars, or the thin gas between them. Most grains are smaller than a grain of sand, and many are only a few micrometers across. They drift through the galaxy in low concentrations, separated by wide distances. At ordinary speeds, a spacecraft may encounter them occasionally. At interstellar speed, however, each encounter becomes a violent transfer of energy, concentrated into a tiny point. The farther and faster the journey continues, the more certain repeated impacts become. Dust grains form in several environments. Some condense in the cool outer layers of aging stars, where atoms combine into solid particles before being carried by stellar winds. Others form in material expelled by supernova explosions. Those strong shocks can also destroy existing grains. Dense molecular clouds allow particles to gather coatings of ice and simple molecules. Over time, grains move through radiation fields, shocks, and collisions that alter their size, shape, and composition. Many grains contain silicate minerals built from silicon and oxygen. Others contain carbon-rich material metals or frozen compounds. Their structures may be compact, porous, irregular, or layered, A fragile grain can break apart easily, while a dense metallic grain concentrates more mass into a smaller area. The danger to a spacecraft depends not only on size but also on composition, angle of impact, relative speed, and the material struck. At low velocity, a grain may scratch a coating pit, a window, or damage an exposed sensor. At higher velocity, the collision becomes more like a small explosion. The grain and part of the target surface can vaporize instantly. The resulting hot plasma expands from the impact point while fragments and shock waves travel through nearby structure. Even when the outer hull is not penetrated, repeated impacts can weaken materials and reduce the reliability of instruments. The energy of an impact rises rapidly with speed. Doubling velocity produces much more than a simple doubling of damage. At a significant fraction of the speed of light, even a microscopic grain carries energy comparable to a powerful conventional explosive concentrated into a tiny area. Such speeds turn the forward direction of travel into the most dangerous surface of the vehicle. Every particle ahead becomes a projectile because the spacecraft brings enormous relative motion into the collision. Detecting grains before impact is extremely difficult. They are small, dark, and scattered through space. Sunlight becomes weak over interstellar distances, and a grain reflects almost nothing toward the spacecraft. Radar requires a transmitted signal to strike the target and return, but the reflected energy from a microscopic grain would be too faint at useful distances. Optical systems may detect larger objects, yet the smallest dangerous particles remain effectively invisible. A spacecraft, therefore, relies mainly on shielding rather than avoidance. The simplest shield is a thick sacrificial layer placed in front of essential systems. It absorbs impacts and can erode gradually over time. More advanced designs use several separated layers. The first layer breaks the grain apart and turns it into plasma and fragments. Empty space allows the debris cloud to spread before it reaches the next layer, reducing the concentration of energy. This arrangement resembles a Whipple shield, a design used on spacecraft near Earth. For interstellar travel, the layers would need to be thicker, stronger, and adapted to much higher velocities. Materials might include metals, ceramics, carbon composites, water ice, or hydrogen-rich plastics. Each material responds differently to heat shock radiation and fragmentation. A useful shield must protect against both solid grains and high-energy gas particles without becoming impossibly heavy. Mass creates a serious trade-off. A thicker shield improves protection, but every additional kilogram must be accelerated to cruise speed. The propulsion system must supply more energy, and later the vehicle must remove that motion if it intends to slow down. Shielding cannot simply be increased without limit. Designers must estimate the expected dust density along the route and choose a level of risk that the mission can carry. Those estimates remain uncertain. Astronomers measure dust through starlight extinction, infrared emission, spacecraft detectors, and samples collected within the solar system. These methods reveal average properties, but they cannot map every grain along a path extending across light years. Local clumps may contain more particles than expected. A route that appears clear from distant observations may still include an undetected concentration. Small impacts also produce secondary hazards. Vaporized material can become electrically charged and interfere with antennas or sensors. Fragments from the shield may strike other parts of the spacecraft. Repeated shock waves can loosen joints, damage cables, or create microscopic cracks. A transparent window exposed directly would gradually become cloudy and weakened. Sensitive instruments may require protective covers that open only during brief observations. The forward shield must also remain aligned with the direction of motion. If the spacecraft rotates unexpectedly, less protected surfaces may face incoming grains. Attitude control, therefore, becomes part of impact protection. Star trackers, gyroscopes, thrusters, and internal wheels must keep the vehicle stable over long periods. A failure in orientation could expose radiators, communication dishes, or habitat walls to a stream of high-speed particles. Repairs are difficult because the damaged region lies at the front of the spacecraft, directly facing the hazard. Robotic systems may inspect and replace outer panels. Stored materials could be melted, printed, or assembled into new shield layers. A crewed vessel may use tanks of water waste or frozen material as part of the protective mass. These resources must remain positioned carefully so that their movement does not disturb balance or reduce life support reserves. Dust may also limit practical cruise speed. Faster travel shortens the duration of radiation exposure and life support demand, but it sharply increases impact energy. A mission cannot choose speed based only on propulsion. It must survive the material environment along the route. Beyond a certain point, stronger shielding may add so much mass that further acceleration becomes inefficient or impossible. Interstellar dust, therefore, transforms emptiness into a field of hidden collisions. Most grains remain unseen, and most of space remains vacant, yet the enormous distance ensures repeated encounters. The threat grows quietly with every increase in speed. Survival depends on layered protection, accurate estimates, stable orientation repair capacity, and enough remaining shield to absorb impacts that cannot be predicted or avoided. Far beyond the protective influence of planetary atmospheres and magnetic fields, deep space radiation becomes a part of the journey. It does not arrive as a storm or a continuous beam. Instead, energetic particles cross the spacecraft, passing through metal insulation, electronics, and living tissue. Some particles come from the sun, but beyond the heliosphere, the dominant background is formed by galactic cosmic rays. Their presence is sparse, yet their energy is high enough to make every impact important. Galactic cosmic rays are mostly protons, which are the nuclei of hydrogen atoms. A smaller fraction consists of helium nuclei, and an even smaller fraction contains heavier atomic nuclei. These heavy particles may include carbon, oxygen, silicon, iron, and other elements. Although rare, they can carry great electric charge and deposit large amounts of energy as they pass through matter. Their biological effect can therefore be much greater than their small number suggests. The exact origins of many cosmic rays are difficult to identify. Magnetic fields throughout the galaxy bend the paths of charged particles, so their arrival direction may no longer point toward the source. Observations indicate that supernova remnants and other energetic environments accelerate many of them. A cosmic ray does not always stop inside the spacecraft. Many pass through several layers and continue outward. Along the way, they ionize atoms by removing electrons. This ionization can break chemical bonds, disturb electronic circuits, and damage biological molecules. A heavy nucleus may leave a dense track of disruption through tissue, affecting many cells along a narrow path. A proton may produce less damage per crossing, but protons arrive more frequently. When a high-energy particle strikes the hull, it can also collide with an atomic nucleus in the shielding. The collision may break that nucleus apart and create secondary particles. These fragments can include neutrons, protons, lighter nuclei, and electromagnetic radiation. Some secondary particles travel deeper into the vehicle than the original particle would have traveled. Shielding, therefore, changes the radiation environment rather than simply removing it. This effect makes material choice important. Dense metals provide strong structural protection and can block lower energy radiation, but they may produce many secondary particles when struck by cosmic rays. Materials rich in hydrogen, such as water and certain plastics, can reduce some secondary radiation more effectively. Hydrogen nuclei have nearly the same mass as protons and can absorb energy through repeated collisions. Water stores food supplies, fuel, and waste may therefore become part of the protective arrangement around occupied areas. No practical shield can stop all galactic cosmic rays. The highest energy particles penetrate large amounts of matter, and adding enough mass to block them would make acceleration extremely difficult. Mission design must balance shielding speed, power, and payload. A protected shelter can reduce exposure during solar storms, but galactic cosmic rays arrive continuously from every direction. The entire living area requires some degree of protection. Radiation exposure accumulates over time. A short mission may accept levels that would become unacceptable during decades or centuries. The effect on the body depends on total dose particle type energy, exposed organs, and individual biology. Cells can repair some damage, but repairs are not always complete. Mutations may remain, and tissues with rapidly dividing cells can be especially vulnerable. Long-term exposure may increase the risk of cancer, cataracts, circulatory disease, and damage to the nervous system. The exact risks of very long interstellar missions remain uncertain because no human population has experienced that environment. Data from astronauts, particle accelerators, medical studies, and biological experiments provide partial guidance. Models must extend those findings across durations, and particle mixtures that cannot be reproduced completely on Earth. The nervous system presents a particular concern because some neurons are not easily replaced. High-energy particles may affect memory, attention, movement, or behavior through direct damage and inflammation. Research continues on how strongly these effects would appear at realistic deep space exposure levels. Radiation also affects reproduction and development. Genetic material in reproductive cells can be damaged, while embryos and growing tissues are sensitive to ionizing radiation. A multi-generational mission would need protected areas for pregnancy, medical monitoring, and careful management of cumulative exposure. Biological diversity would also require preservation through stored cells, embryos, or genetic records, all of which must remain shielded and functional for long periods. Electronic systems face parallel risks. A particle crossing a computer chip can change the electrical state of a memory cell or logic circuit. This event may corrupt data, alter a command, or cause a temporary failure. More severe impacts can damage transistors permanently. Repeated exposure also changes insulating layers and semiconductor structures, slowly reducing performance. Engineers use radiation-hardened components, error-correcting memory, duplicated computers, and automatic recovery procedures. Critical calculations may be performed by several processors and compared. Data may be stored in multiple locations. Systems can restart after detecting abnormal behavior. Sensors are also vulnerable. Radiation can create false signals in cameras, particle detectors, and navigation instruments. Optical devices may develop damaged pixels. Solar cells lose efficiency, though sunlight is already too weak for major power production. Insulation may become brittle, and lubricants may change chemically. The spacecraft must distinguish between a real change outside and an error produced by radiation inside its own instruments. Active shielding has been proposed as an additional defense. Magnetic or electric fields could deflect charged particles before they reach the hull. In principle, this resembles the way planetary magnetic fields redirect part of the solar wind. In practice, the required field structures and power may be enormous, especially for high-energy particles. Such systems would not easily stop neutral particles and could create complicated radiation patterns around the vehicle. Deep space radiation cannot be avoided by choosing a clear route. It fills the galaxy and changes only gradually with location, magnetic conditions, and stellar activity. Faster travel reduces the time of exposure, but faster motion increases the danger from gas and dust impacts. Slower travel eases some propulsion demands while allowing radiation damage to accumulate. The threat is therefore continuous, invisible, and deeply connected to duration. Every particle leaves a small trace, and every year adds to the total. The spacecraft must protect tissue, preserve electronics, replace damaged components, and monitor health without expecting the environment to become safer. Across interstellar distance, radiation turns time itself into one of the central hazards of travel. Far from the sun, Navigation loses the familiar geometry of planets, moons, and nearby radio beacons. The spacecraft moves through a field of distant stars that appear almost fixed, while its own position changes across distances too large for ordinary intuition. No road marks the route, and no visible line connects departure with destination. Guidance depends on measurements, clocks, stored maps, and repeated corrections made with very limited certainty. Near Earth, navigation can use radar, satellites, ground stations, and well-known orbital paths. In interstellar space, those references become faint or useless. The Sun shrinks into one star among many, and Earth cannot be resolved directly by ordinary cameras. Radio signals from home arrive weekly after long delays. The spacecraft must determine both where it is and how it is moving without relying on constant help. Star trackers remain one of the most reliable tools for orientation. These cameras observe patterns of stars and compare them with a stored catalogue. Because stars lie at enormous distances, their relative arrangement changes very slowly. The system can calculate the direction in which the spacecraft points, allowing antennas, shields, radiators, and instruments to remain aligned. Orientation, however, is not the same as position. A vehicle may know exactly where it faces while remaining uncertain about its location along the route. Position can be estimated by measuring angles to nearby stars. As the spacecraft moves close, stars shift slightly against the more distant background. This apparent shift is called parallax. The same principle allows astronomers near Earth to measure stellar distances. In interstellar travel, the spacecraft can observe parallax from a changing location and compare the result with stored maps. The method becomes more useful near a destination star where angular changes grow larger. The accuracy of parallax depends on precise instruments and reliable knowledge of stellar motion. Stars do not remain fixed. Each one moves through the galaxy with its own velocity, and a journey lasting centuries requires maps that predict those changes. Some stars have unseen companions that alter their apparent positions. Others change brightness or produce activity that complicates measurement. Navigation software must account for these effects and update its model as observations accumulate. Pulsars provide another possible reference. A pulsar is a rapidly rotating neutron star that sends beams of radiation through space. When a beam crosses the spacecraft, instruments detect a regular pulse. Different pulsars have distinct timing patterns and positions. By comparing the arrival times of pulses from several sources, the spacecraft can estimate its location and correct its onboard clock. This method resembles navigation by distant natural beacons. Pulsar timing is stable but not perfectly simple. Some pulsars gradually slow as they lose rotational energy. Sudden changes called glitches can alter their pulse rate. Interstellar gas can delay radio pulses differently according to frequency. X-ray pulses pass through gas more easily, but X-ray detectors require sensitive equipment and careful shielding. The spacecraft must compare observed timing with long-term models that may need revision. Inertial navigation supports these external measurements. Gyroscopes and accelerometers track changes in rotation and motion from a known starting state. In principle, adding every measured acceleration reveals the new position and velocity. In practice, tiny errors accumulate. A slight bias in a sensor, unnoticed vibration, or small thermal effect can produce a growing difference between the estimated path and the true one. Over light years, even minute drift becomes significant. The spacecraft also experiences forces too small to notice during short missions. Heat leaves different surfaces unevenly and produces a weak recoil. Gas may escape through valves or microscopic leaks. Dust impacts transfer momentum. Internal mechanisms move mass from one place to another. Radiation from stars exerts pressure on exposed surfaces. Each effect can alter velocity by a tiny amount. Navigation systems must estimate these forces rather than assume perfect coasting. Course corrections require propulsion. Small thrusters can change direction or speed, but every burn consumes limited fuel or stored energy. A correction made early usually requires less effort than one made late. The spacecraft, therefore, compares many observations before deciding whether an apparent error is real. Too little correction allows drift to grow. Too much correction wastes resources and may introduce new errors. Aiming at another star is more difficult than pointing toward its present location. The target moves during the journey, and the spacecraft must travel toward where the star will be at arrival. Its planets also move around it. If the mission seeks a particular planet, the final path must account for the star's motion, the planet's orbit, and the time required for slowing. Uncertainty in any of these values widens the possible arrival region. Light itself carries delayed information. A star observed from many light years away appears as it existed years earlier. Its measured position reflects that earlier state, not the moment of observation aboard the spacecraft. Astronomers calculate forward using known motion, but every measurement contains uncertainty. Over a long journey, predictions must be refined from closer observations. The vehicle gradually replaces old maps with more direct knowledge. Autonomy becomes essential because Earth cannot guide each decision. The spacecraft must identify stars, reject false signals, diagnose damaged sensors, and choose safe corrections. Redundant instruments compare results. If one star tracker is blinded or degraded, another may take over. If pulsar timing becomes unreliable, optical observations may provide support. Navigation depends on several methods rather than one perfect system. For a crewed mission, human judgment may assist, but people also depend on machines for measurements too precise to perform unaided. Generations may pass while the route continues. Training records and calibration procedures must survive cultural and technical change inside the vessel. A forgotten error in a star catalogue or an incorrect assumption in software could persist for decades before becoming visible. The farther the spacecraft travels, the less useful its departure references become. Navigation turns into a continuous reconstruction of position from faint signals and imperfect models. No single observation provides complete certainty. Safe travel depends on patient comparison, stable clocks, accurate maps, reliable propulsion, and the ability to correct small errors before distance magnifies them beyond recovery. A minor deviation left unattended can become a miss, measured in millions of kilometers, leaving no atmosphere, ocean, or wide planetary surface available to absorb the remaining navigational error safely. Interstellar distance changes communication from conversation into delayed exchange. Near Earth, a signal crosses space quickly enough for engineers to respond within seconds or minutes. Farther away, the same signal requires hours, then days, then years. Nothing is wrong with the transmitter or receiver. The delay comes from the finite speed of light, which no radio message can exceed. As distance grows, mission control can no longer guide events while they happen. Radio waves and laser beams both travel at the speed of light in vacuum. A spacecraft 1 light-year from Earth receives a command 1 year after it is sent. Its reply takes another year to return. A complete exchange, therefore, spans at least 2 years even before anyone studies the data or prepares a response. At several light years, the delay becomes part of the mission's structure rather than a temporary inconvenience. The signal also weakens as it spreads. A radio transmission leaving an antenna expands across a widening region of space. Only a small fraction reaches the receiving antenna. Greater distance requires larger dishes, more precise pointing, stronger transmitters, longer listening periods, or lower data rates. Each improvement demands mass power, stability, and maintenance. A spacecraft cannot increase these resources without limit. Antenna alignment becomes critical. A narrow beam carries energy more efficiently, but it must point accurately toward Earth's predicted position. Earth moves around the Sun, and the Sun moves through the galaxy. The spacecraft also changes position while its signal travels. Navigation software calculates where the receiver will be when the beam arrives. A small pointing error can send the transmission into empty space, leaving no indication that contact was attempted. Lasers can produce narrower beams than radio antennas and may support higher data rates. They also require extremely accurate pointing. Dust vibration, thermal expansion, and mechanical drift can shift the beam. A telescope used for communication must remain clean, stable, and correctly shaped for decades or longer. A damaged mirror or failed pointing mechanism can reduce contact even when the power source still operates. Interstellar dust and gas usually do not block communication completely, but they can scatter or absorb some frequencies. Plasma between stars can delay radio waves by different amounts depending on wavelength. Charged particles near a star can add noise and distortion. Mission systems may transmit across several frequencies so that receivers can compare signals and correct some effects. This redundancy consumes extra time and power. Data cannot be sent without restriction. Scientific instruments, medical systems, navigation, sensors, and habitat computers may produce enormous amounts of information. The communication link may carry only a small portion. The spacecraft must decide what to keep, compress, summarize, or discard. Raw measurements may remain aboard while selected results travel to Earth. A mistake in this process can remove information that later becomes important. Error correction becomes essential because faint signals arrive mixed with background noise. Messages include repeated patterns and additional information that allows missing or altered bits to be reconstructed. The receiver may combine many weak transmissions into a reliable result. This method improves accuracy but lowers the effective data rate. A detailed image, medical record, or engineering archive may require days or months of transmission. Power limits every contact. A strong transmitter consumes energy that might otherwise support life support, heating, propulsion control, or repairs. The spacecraft may store power and communicate during scheduled periods. Between contacts, the antenna may serve other tasks or remain inactive. If the power system weakens, communication may become shorter, slower, and less frequent long before the mission itself ends. The growing delay removes immediate supervision. Earth cannot notice a failing pump and send instructions before the cabin changes. It cannot guide a sudden avoidance maneuver, respond to a medical emergency, or correct a computer error in real time. By the time a warning reaches Earth, the spacecraft has already managed the event or suffered its consequences. Any later advice addresses a situation that may no longer exist. Autonomous systems therefore monitor pressure, temperature, power, radiation, navigation, and structural health continuously. They compare measurements with safe limits and take action when conditions change. A leak may trigger isolation of a compartment. A computer fault may cause a restart or transfer of control. A navigation error may lead to a correction after several independent checks. These actions must be reliable because confirmation from Earth arrives too late. Autonomy creates its own danger. Software cannot anticipate every combination of failures. A protective response may preserve one system while damaging another. A computer may misinterpret a faulty sensor as a real emergency. Artificial intelligence can compare patterns and propose solutions, but its conclusions depend on training hardware and data that may become outdated during a long mission. Human crews must understand enough to challenge automated decisions. Records from Earth remain valuable, yet they describe a world that continues changing. Scientific knowledge, medicine, engineering languages and institutions may develop during the years between messages. A spacecraft receives updates long after they are created. Earth receives reports from conditions that existed years earlier. Both sides communicate with versions of each other preserved by distance. Emotional communication changes as well. Messages from family institutions or later generations arrive without the possibility of immediate response. A sender may be much older before an answer returns. Some people may no longer be alive when their messages are received. Crews must treat communication as correspondence across time rather than shared presence. The psychological effect may remain profound even when regular signals continue. A lost link cannot be repaired from Earth. The spacecraft must diagnose its transmitter antenna power supply and pointing system alone. Spare components may be installed by robots or crew members. Backup antennas can preserve a slower channel. If every long-range system fails, the vessel continues in silence. Earth may never learn whether the cause is damage, power loss, navigation error, or complete mission failure. Communication at interstellar distance therefore becomes fragile, delayed, and selective. It carries information, but cannot provide rescue, immediate control, or shared time. The spacecraft must function as an independent world while faint signals cross the darkness behind it. Contact remains possible only through careful pointing, durable hardware, limited power, patient error correction, and acceptance that every message belongs to a past that neither side can change ever again. A journey lasting longer than a human lifetime changes the spacecraft from a vehicle into an inhabited world. Its passengers cannot depend on stored supplies alone because food, water, air, medicine, tools, and knowledge must remain available for generations. Every essential resource has to circulate through systems that recover and reuse it. The habitat must support survival, birth, childhood, work, illness, aging, and death while remaining sealed within interstellar space. Air management begins with oxygen and carbon dioxide. People consume oxygen and release carbon dioxide through breathing. Plants can reverse part of this exchange through photosynthesis using light to build tissue and release oxygen. Mechanical systems also remove carbon dioxide through chemical filters and restore oxygen through electrolysis, a process that splits water into hydrogen and oxygen. A reliable habitat would likely combine biological and mechanical methods because either may fail or become unbalanced. Water must circulate almost completely. Moisture from breath, sweat, washing, food preparation, and waste can be collected and purified. Urine can be processed to recover most water, while solid waste can be treated for useful nutrients. Small losses still matter. A leak that removes a little water each year becomes serious across centuries. Tanks, pipes, seals, pumps, and filters therefore require inspection, replacement, and manufacturing from onboard materials. Food presents a deeper challenge. Stored meals lose quality over time and become impractical for a long voyage. Most food must be produced within the habitat. Crops need light, water, carbon dioxide, nutrients, controlled temperature, and growing space. Different plants provide carbohydrates, proteins, fats, vitamins, and fiber. A stable system also requires crop diversity because disease or equipment failure could destroy one variety. Artificial lighting can support growth without sunlight, but it consumes power and produces heat. Every lamp pump fan and nutrient system becomes part of the food supply. Plants release moisture and gases that affect cabin conditions. Roots depend on oxygen and careful nutrient balance. Pollination may require insects, air movement, or mechanical assistance. Seeds must remain healthy across repeated generations while seed banks protect against crop loss. Animals could add dietary variety, but they require food-water space and waste processing. Small organisms may be more efficient than large livestock. Fish insects, fungi, algae, and cultured cells could provide protein using fewer resources. Even then, each biological system introduces disease risks and ecological interactions. The habitat cannot allow one species to spread without control or disappear unnoticed. Waste becomes a resource, not discarded material. Plant remains human. Waste-damaged food and biological materials contain carbon, nitrogen, phosphorus, and other elements needed for new growth. Microorganisms can break these materials down, returning nutrients to the system. The process must prevent harmful microbes, toxic compounds, and imbalances. A closed ecosystem is not a self-correcting forest. It is an engineered cycle requiring measurement and active control. Medical care must operate without evacuation. Injuries, infections, dental problems, childbirth, chronic disease, and surgery all occur within the vessel. Equipment wears out, medicines expire, and specialists may not always be available. Medical knowledge must be stored, taught, and practiced continuously. Automated diagnostic tools may assist, but trained people remain necessary for judgment and care when systems fail. Medicines could be produced from stored chemicals, engineered microorganisms, or small manufacturing systems. Sterile supplies need protected storage and reliable replacement. Imaging equipment, laboratory instruments, and surgical tools require calibration and repair. A generation that neglects medical training may leave the next vulnerable even if the original records remain intact. Genetic health becomes important in a small population. Limited numbers increase the chance that harmful inherited traits appear more often over generations. A mission may preserve genetic diversity through a larger founding population, carefully planned reproduction, and stored sperm eggs, embryos, or genetic material. These methods reduce risk, but they also require refrigeration, ethical rules, expertise, and long-term records. Radiation can damage reproductive cells and stored biological samples. Protected vaults must remain deep within water-food, structural mass, or dedicated shielding. Pregnancy and childhood may require areas with lower exposure because developing tissues are sensitive. Health monitoring must follow changes across generations rather than treating each person as an isolated case. Gravity also affects development. Continuous weightlessness weakens bones and muscles and changes circulation. Children raised without normal gravity may develop in ways that remain uncertain. Rotating sections could create artificial gravity through circular motion. The habitat would need a radius and rotation rate that provide useful force without causing severe motion effects. Bearings, seals, and structural joints would operate for centuries and require replacement. Maintenance becomes a permanent culture. Every pump, wire, computer, pressure wall, radiator, and bearing eventually degrades. Spare parts alone cannot cover centuries of failure. The spacecraft needs workshops to refine materials, manufacture components, and recycle damaged equipment. Some parts require metals, ceramics, plastics, electronics, and precise tools. The production system itself must also be repaired. Knowledge must survive as practice, not merely as stored data. People must understand agriculture, medicine, engineering, navigation, ecology, and governance. Education becomes essential infrastructure. Records need repeated copying into new formats as computers and languages change. Skills that are not used may disappear, so training must continue during long periods without crisis. Social stability is equally necessary. A closed population has limited space-fixed resources, delayed communication, and no practical option to leave. Rules for work, reproduction, conflict, privacy, leadership, and resource use must remain accepted across generations. Systems that depend entirely on obedience may fail when values change. Systems allowing unlimited choice may threaten shared survival. The habitat must balance individual life with collective responsibility. Mental health depends on meaningful work. Relationships, rest, personal space, and connection to a wider purpose. Artificial environments can provide changing light, plants, art, exercise, and quiet areas. Still, every horizon remains manufactured, and every person belongs to the same society. Conflict cannot be escaped by distance. Grief, boredom, inequality, and loss of trust may become as dangerous as mechanical failure. A multi-generational spacecraft survives only when biology, technology, and culture remain linked. Air supports crops, support people, waste supports new growth, education supports maintenance, and social order supports every cycle. Failure in one area spreads into others. The farther the vessel travels, the more completely it must become its own enduring world, carrying life and the capacity to renew it without outside rescue or replacement indefinitely. Approaching another star system begins long before the destination star appears large. For most of the journey, it remains a bright point against the background, slowly changing position as the spacecraft closes the distance. Its light grows stronger, but the increase is gradual across years. The vehicle enters a region where the star's gravity, radiation, magnetic activity, and surrounding material become increasingly important. Every measurement helps replace distant estimates with direct knowledge, yet uncertainty remains because no previous spacecraft has mapped the system from nearby. The star's motion must be understood with great precision. It travels through the galaxy while the spacecraft approaches and its planets move around it on separate orbits. Earlier observations from Earth provide estimates of mass, brightness, age, and possible companions. Those measurements are limited by distance and viewing angle. As the spacecraft draws closer, its cameras and instruments refine the star's position, velocity spectrum, and activity. Navigation software updates the expected arrival path continuously. Starlight becomes a major environmental force again. Solar panels may return to useful operation if the star resembles the Sun, but their output depends on distance, stellar type orientation, and surface condition after the long crossing. A hotter star releases more ultraviolet radiation, while a cooler star provides less visible energy. The spacecraft must adjust thermal control as external heating rises. Surfaces that remain cold for decades may warm unevenly, creating stress in joints, coatings, cables, and seals. The star may also produce flares, winds, and energetic particles. A quiet appearance from Earth does not guarantee a quiet local environment. Small red stars can release powerful flares even when their ordinary light is faint. Larger stars may produce strong ultraviolet radiation and dense stellar rings. Instruments measure charged particles and magnetic fields as the spacecraft enters the star's outer influence. These conditions determine how much protection electronic sensors and living areas require. The system's structure may be only partly known. Bright planets can sometimes be detected from Earth through their gravitational effect on the star or by the slight dimming produced when they cross its face. Smaller planets, moons, rings, asteroids, and comets are harder to identify. Their orbits may also be inclined in ways that hide them from earlier observations. The approaching spacecraft must treat the region as incompletely mapped. Dust becomes more concentrated near a planetary system than in the emptier space between stars. Some grains occupy broad disks formed from collisions among asteroids and comets. Others follow elongated orbits or drift under radiation pressure and stellar wind. At high approach speed, even a modest increase in dust density raises danger sharply. Forward sensors search for scattered light and thermal emission, but small grains remain difficult to detect individually. Larger bodies are easier to see, yet their paths require time to determine. A single image shows position, but not a complete orbit. Repeated observations reveal motion, allowing the spacecraft to estimate direction and speed. During rapid approach, there may be limited time to gather enough data. Autonomous navigation must identify hazards, compare possible routes, and preserve a clear corridor without waiting for instructions from Earth. Gravitational forces also become more complex. Far from the system, the destination star acts almost like a single point of mass. Closer in planets and companion stars create additional pulls. These forces may be small at first, but they alter the path over time. A hidden giant planet could shift the expected trajectory or disturb smaller bodies into unusual orbits. Precise tracking of background stars helps reveal these changes. Slowing is one of the greatest challenges. A spacecraft that crosses interstellar distance quickly carries enormous kinetic energy. It cannot simply arrive and stop. Engines must produce thrust opposite the direction of motion, often for months or years. Every unit of propellant used for braking had to be accelerated during departure, increasing the original energy demand. A mission designed only for a fast flyby avoids this burden but receives little time for close observation. Several braking methods have been proposed. Conventional propulsion carries fuel and expels mass to reduce speed. Electric propulsion uses smaller forces over long periods but requires sustained power. A magnetic sail may interact with charged particles in the stellar wind, while a light sail may use pressure from the star's radiation. These methods remain technically difficult and depend on local conditions that may not match predictions. Failure to slow at the planned rate can leave the spacecraft passing through the system too quickly. Braking also changes impact risk. As speed falls, collisions with gas and dust become less energetic. Before that reduction occurs, the spacecraft remains exposed while entering a region with more material. The forward shield must survive the most hazardous part of the approach, just as propulsion and navigation become most demanding. Damage to engines, radiators, or sensors during this period could prevent successful deceleration. Communication with Earth now spans years. Mission planners can provide broad goals, but every immediate choice belongs to the spacecraft. It must decide when to begin braking, how to respond to unexpected planets, and which route offers the lowest risk. Delayed information from Earth may improve scientific interpretation, but it cannot guide a sudden maneuver. The vehicle's stored models and current observations carry greater authority than old predictions. For a crew, the destination star may become emotionally important, yet the physical environment remains uncertain. Increased light does not guarantee warmth, breathable air, or safe worlds. Radiation may rise and navigation demands may intensify. The habitat must remain closed and stable throughout the approach. Food production, medicine, maintenance, and social order cannot pause while attention shifts outward. Approaching another star system therefore concentrates many risks into one region. The spacecraft leaves the relative uniformity of interstellar space and enters a changing field of light. Gravity, particles, dust, and hidden orbits. Every kilometer provides better information, but every kilometer also reduces the time available to respond. Success depends on careful braking, continuous mapping, stable shielding, autonomous judgment, and machinery that still functions after the long crossing. The destination is no longer a distant point, yet it offers no safety. Its unseen architecture must be discovered while the vessel is already committed to arrival. Distance has narrowed, but uncertainty has become more immediate, surrounding every correction with consequences that cannot be reversed once the path grows short. Reaching the target world does not end the interstellar journey. It replaces distant uncertainty with conditions that cannot be ignored or escaped. The planet now fills instruments with details unseen by earlier telescopes. Clouds, surface colors, atmospheric gases, magnetic fields, moons, rings, and debris become measurable. Every observation influences whether the spacecraft remains in orbit, attempts a landing, or avoids the world entirely. Arrival becomes a sequence of decisions made without assistance from Earth. The planet's orbit must be known precisely. After entering the system, small errors in position and velocity can carry it past the intended world. Optical cameras track the planet against background stars, while radar or laser ranging may estimate distance at close range. Navigation computers combine these measurements with the gravity of the star, nearby planets and moons. Course corrections become smaller but more urgent because little time remains for another attempt. Orbital insertion requires the spacecraft to lose speed. An engine burn performed too early, too late, or in the wrong direction can produce a wide orbit, a collision, or an escape back into interplanetary space. The engine must operate after years or centuries of storage and use. Valves must open, fuel must flow, and guidance systems must remain stable while thrust changes the vehicle's path. A partial failure may leave the spacecraft in an orbit that cannot support the mission. Some worlds possess atmospheres that can help reduce speed. A spacecraft may pass through the upper air so that drag removes part of its motion. This process is called aerobraking. It saves propellant but creates heat and structural stress. Atmospheric density may vary with weather season, altitude, and stellar activity. A layer that appears thin from distant measurements may become dense enough to overheat the vehicle, while an atmosphere that is thinner than expected may provide too little braking. Before any landing, the spacecraft must map the surface. High ground, deep basins, ice fields, loose dust, steep slopes, and hidden rocks all affect safety. Clouds may block cameras, while haze may distort distance measurements. Radar can see through some clouds and reveal broad terrain, but it may not identify every small hazard. A landing site that appears smooth from orbit may contain fractures or soft material unable to support the vehicle. The atmosphere itself may be hostile even when it appears familiar. Oxygen can support breathing, but high concentrations increase fire risk. Carbon dioxide can become toxic. Nitrogen, methane, sulfur compounds, or unknown aerosols may affect lungs, materials, and equipment. Pressure may be too low to sustain the body, or so high that structures require heavy reinforcement. Temperature may change sharply between day and night or across seasons. Wind may carry abrasive dust or corrosive particles. Liquid water does not guarantee safety. It may contain salts, metals, reactive chemicals, or unfamiliar microorganisms. Ice may trap gases or unstable compounds. Rivers and oceans may exist beneath conditions unsuitable for human biology. Every sample must be isolated and studied before it enters the habitat. Filters, sterilization systems, and sealed laboratories protect both the crew and the planet from contamination. Planetary protection works in both directions. Earth organisms carried on the spacecraft could spread into a native environment and alter it before scientists understand what is present. Microbes can survive in cracks, equipment, water systems, and dormant spores. Cleaning before launch reduces this risk, but may not remove every organism. After a long voyage inside an inhabited spacecraft, complete sterility becomes impossible. Landing plans therefore require strict separation between living quarters, laboratories, waste, and the outside environment.